Greetings and welcome back. Today we'll be looking at the formation of imines. Imines are similar to amines, but imines have a C double bond N instead of a C single bond N. So today we'll be looking at the way that we can form imines. Before we get into imines, we're going to look at the way that we can form acetals or ketals again. We make acetals or ketals from carbonyl-containing compounds, so C double bond O's. You may remember that when we're doing this, we add an alcohol, let's say in this case ethanol, in the presence of acid, and more or less we are adding the oxygen of the alcohol and removing a bond to the oxygen in the carbonyl. That gives us, after a whole lot of kind of tidiness with acids and bases, a hemiacetal, in which we have one bond from that carbon to the pre-existing oxygen and one bond to that new chunk over there, right here. Then what we can do is add in, well, we don't have to add anything else in, but that nucleophile, the alcohol, can attack again and kick off that OH, which really gets protonated first. So this is not truly the mechanism, it's just kind of the shorthand mechanism. And that will allow us to attack that, or attach that second OR, making a second ether, which results in the loss of water. All right, so we've done this previously. This is how we form acetals or ketals. Notice that when we're doing this, the first time we attach that big O ethyl group, the second time we attach another one. Over the process of this, the oxygen right here joins on and loses an H. It only has one H to lose, and besides this R group, it can only make one more bond to that carbon. And therefore, it does make one more bond to that carbon. If we want to kick off the OH completely, though, we can't make another bond to this oxygen because this oxygen already has two bonds to carbon. Therefore, we have to add in another oxygen via another alcohol. And that's how we get two alcohols attached. All right, so fast forward to the present. In order to make an imine, we go through a reaction that is almost exactly the same in terms of its mechanism. We start with a C double bond O, but instead of adding two alcohols, we add one ammonia or primary amine. A primary amine, to jog your memory, is an NH2 attached to one R group. So it's primary because it has one carbon directly attached. All right, so over the course of this mechanism, which I won't draw for you now because it's the same as the acetal, we would protonate this oxygen to make it make the carbon a better electrophile. We would attack it with that nitrogen, and what that would do is allow us to make something that halfway through would look a lot like a hemiacetal. You would have an NH attached. However, instead of then attaching a second amine, what we would do is protonate, at this point I will get into the exact mechanism, we will protonate that oxygen, which would turn that group up there into an OH2+, which is a good leaving group. And then the nitrogen has another lone pair. So instead of waiting around for a second amine to come in, the current amine that is attached can just share a second pair of electrons down there and kick off that water. That would give us a C double bonded to that N with a plus charge and an H attached. And using some of the amine that we have in solution already, in this case an ethylamine, this guy can remove that extra H and would give us, at the end of this reaction, a C double bond to an N. And that would be neutral. So what we can see is that overall, an imine formation involves taking this oxygen off and forming water. You'll notice that water came out at this point right here. Just in the same way that when we formed an acetal or a ketal, we took off that oxygen as water at the very end. But instead of replacing this double bond O with two different bonds to alcohol, we replace a double bond O with a new double bond to nitrogen. And this right here is an imine, and so all that we have done is added on this group right here, but effectively, because nitrogen, a primary amine or ammonia, can remove two hydrogens, we make a double bond to the exact same nitrogen, and that is it. So it turns out that this will work with really any NH2 attached to whatever. So I'm going to give you some examples of that. If we start with, let's say, this aldehyde right here, and add NH3 in the presence of a little bit of acid, we would be able to take this oxygen off and replace it completely with an N. The oxygen comes off as water, meaning that we need to lose two of the hydrogens from our ammonia. We would end up with the same carbon backbone, but instead of a double bond O, we would have a double bond N. Since we would remove two of the hydrogens from ammonia, we would have one hydrogen left over, and we would generate, in this case, in all of these cases, water. So this is a condensation reaction. If you wanted to push this reaction backwards, you would just add a lot more water, and through hydrolysis, go back to where you started. So, hydrolyzed, these can be hydrolyzed the exact same way that they are when we take acetals backwards. All right, so we could also start with, let's go with this ketone. I'll draw this one upside down. You're welcome. And we could add in, let's say, NH2, This might look a little bit odd, but really you're doing the exact same thing. We're going to attach on this nitrogen right here, and it's going to lose two hydrogens, and it will go in place of the oxygen. So we'll turn our C double bond O into a C double bonded to N. There would be another NH2 still attached. It would just be hanging on. And in this process, what we have removed is yet again water. So just kind of like we did with the acetal, more or less, your nitrogen attacks once, making an alcohol, and then it attacks again, kicking the oxygen completely off. So we're effectively just adding this twice instead of adding two alcohols like we do when we make an acetal or a ketal. So if I started with formaldehyde, I could react it with, let's say, NH2OH. And again, this looks a little bit crazy, but nitrogen is going to be a better nucleophile, and therefore, when it attacks, we will add this guy on twice, once, twice, and essentially kick that oxygen off. Yes, there's a much longer mechanism with a lot of acid and base. Oops, this should always be done in the presence of acid. And we would turn our C double bond O into a C double bonded to N. In this case, we would have an N with an OH coming off of it, because this nitrogen right here had an OH coming off of it. Once again, we would kick off water. And that's about it. We can turn really any C double bond O into pretty much any C double bond N, as long as that N has two hydrogens attached. So let's try one example of that. All right, so let's consider these reactions in reverse. I mentioned this, but I think it's fair to show it to you. If we start off with any ketal or acetal, we can add a bunch of water in the presence of H+, and what happens is that that water effectively comes in twice and is going to kick off both of those alcohols. Doing that exact reaction in reverse, we would remove this guy, and we would convert it back to a ketone or an aldehyde, in this case a ketone. And the same thing goes for the amine. Right now what we're doing is looking at the exact reaction that we just did, only in reverse. So if we started off with, say, C double bond N in this form, this imine specifically, and we added in water and acid, it would push this reaction backwards. Backwards compared to what we were doing previously. It would add on the water and take off this whole chunk right here. So in the same way that we can turn a C double bond O into a C double bond N, we can turn a C double bond N into a C double bond O. That would also kick off NH2 attached to a benzene ring, just like the ones up above. If I kicked off these two molecules, I would generate ethanol. So these molecules don't know in which direction we intend to go. They just know they'll go in the direction that Le Chatelier's principle pushes them, depending on what you add more of. So, in other words, if we start with a ketone or aldehyde, and you add excess alcohol with acid, it'll push the reaction towards the acetal. If you start with an acetal and add a lot of water, it'll push the reaction back to the ketone, or the aldehyde. If we start with an imine, a C double bond N, and add water and acid, we can push it towards the carbonyl. But if we start with a carbonyl and add more ammonia, or take out the water, we can push it back this way towards the N. And so these are completely reversible reactions, and hydrolysis is the name of the reaction that takes them backwards, because we're using water to lyse or cut them. So this is hydrolysis, and this is hydrolysis as well. And that's it. Let me give you an example to try. And thank you very much. I'll see you in class.